Hi, welcome to video 9.8c, term-by-term differentiation and integration. Before we get into this, what we're doing here is creating series from another series. So far what we have is the actual table version of doing it, which is actually figuring out all those derivatives, which are the numerators of the coefficients, etc. But once you have certain series that you can differentiate them or integrate them to get series for others functions. So here's what the property says. If the function given by f of x equals summation, and they're going to do a Taylor just because it's easier, because Maclaurin's is just a Taylor, where c equals 0. Okay, this is the expansion of it, and of course they're just copying out on the coefficient. The coefficient is, f, the 0th derivative at c over 0 factorial. This is the first derivative at c over the 1 factorial, second derivative at c over 2 factorial, etc. And they're saying if that function has a radius of convergence of capital R greater than 0, then on the interval just to the left and the right of c, f is differentiable and therefore continuous. Moreover, the derivative and the antiderivative are as follows. And the key thing is that the radius of convergence of the series obtained by differentiating or integrating a power series is the same as that as the original power series. The interval of convergence, however, may differ as a result of the behavior at the endpoint. So the basic bare bones of the interval of convergence will be the same. You just might or might not include the endpoints. But if you look at these, they'll see f of x equals f prime of x equals integral of f of x dx equals. So for the derivative, keep in mind that your an is a coefficient, it's a constant, and this is your variable term, x minus c to the n. So if you think of taking the derivative of this, you're going to have a constant, which is an, and then you're going to take the derivative of x minus c to the n, which is n times x minus c to the n minus 1. And then it's just times 1 because that's just 1x minus a constant. Now, you will notice here that this says n goes from 1 to infinity. What happens is, that's because the first term here is a0 times x minus c to the 0 over 0 factorial, which is a0 times 1 over 1. And the thing is, when you take the derivative of that first term, the derivative of that first term being a constant is 0. So really, when you take the derivative, you have 0 plus, and then this is a1 times x minus c, so the derivative of that is a1 times 1, and there's your first term. And that's why that begins at 1. Would it be wrong to start it at 0? Not really, because what would happen is that would mean that if n started at 0, this would be 0 times, and then who cares what, because it'll end up being 0. Okay, when you integrate it, now you're integrating it. So if you think of integrating it, there's the famous plus c, because it's an indefinite integral. There's no limits of integration. And then what's going to happen is you're going to integrate this. Well, of course, you're going to pull out the an, and then you're going to integrate x minus c to the n, which will give you x minus c to the n plus 1 over n plus 1. Here, however, you'll notice it stays at 0. And I'll come back to that in a second. Now, if I integrate term by term, apart from the plus c, okay, you're going to integrate a0 dx, which means you're going to have a0 times x minus c. And of course, instead of x everywhere, it's x minus c, right? And then you're going to have a1, and then you're going to integrate x minus c to the 1, which will give you x minus c to the 2 over 2. And then you're going to have a2, and then you're going to integrate x minus c to get x minus c cubed over 3. Now, as far as the lower limit of summation, whether it's 0 or whether it's 1, the way I approach it is I leave it blank. I do the term by term, and then after I've seen the term by term, I just make sure I start somewhere so I don't have a first term of 0. And again, the emphasis is not only are you able to create a new series easily by either differentiating term by term or integrating term by term, but the radius of convergence will be the same, and the interval of convergence will be the same, except for possibly it might differ at the endpoints. Okay, so here's an example in numbers 45 through 48. It says find the intervals of convergence for f of x, f prime of x, f triple prime of x, sorry, double prime, and the integral of f of x dx. Include a check of convergence at the endpoints. Okay, so there's two things we're going to be doing here. Is we're going to be getting a new series and as well determining the intervals of convergence. So here's number 46, okay? So first of all, the whole thing here is your AN. Your UN is the part that doesn't have any x's in it at all, which is this part right here, negative 1 to the n plus 1 over n times 5 to the n. So like we've always done, what we're going to do here is do the ratio test on the original function, and then we're in part B, we're going to find the first derivative, and part C, the second derivative. So we're going to do the ratio test. The negative ones disappear because of the absolute values. Remember, it's un plus 1 over un, so multiply by the reciprocal of un, etc., etc. You're left with x minus 5 to the 1. You pull it out in absolute values. Here you're left with n over 5 times n plus 1. The limit of that limit at infinity is 1/5, and you're going to isolate the absolute value. Your radius of convergence is 5. Now, that's going to be the same radius of convergence for f, f prime, f double prime, f triple prime, the integral, all of them. As far as radius of convergence, you put x minus 5 between negative 5 and 5. That gives you x is between 0 and 10. And now we got to check what happens at 0 and check what happens at 10. Okay? Turns out if you replace the x by 0 in the original series, this will be 0 minus 5, which is negative 5 to the n. So what you do is rewrite that as negative 1 to the n times 5 to the n. This becomes negative 1 to the 2n plus 1, which is always odd, so that's just going to be negative 1. The 5 to the n's cancel, and you're left with negative 1 times the harmonic, which is divergent. Replace x by 10, then that x minus 5 becomes 10 minus 5, or 5. The 5 to the n's cancel. It's an alternating series. Sure enough, the limit as n goes to infinity of your an is 0, and so it converges at 10. So at 0, it diverges. At 10, it converges. Okay, so for f prime of x, here's f of x again, and here's the first few terms of f of x. For the derivative, of course, what's going to happen is this whole thing is this big peanut thing here is just a constant, so that just pulls out. What you're actually integrating is the x minus 5 to the n, sorry, differentiating, which is n times x minus 5 to the n minus 1. The n's cancel, and if you write out the first, from here, not from here, but from here, if you write out the first few terms, notice how I leave this blank. So if I differentiate, that's going to be 1/5 times 1. The next one will be minus 2 over 50, which is 1/25 times x minus 5 to the 1. Then here you'll bring the 3 in front. The 3's will cancel. You'll be left with 1 over 125, x minus 5 squared, etc. The key thing is, now they might ask you for the first 3 terms. They might ask you for the summation notation. But I would always write out at least the first 3 terms. But the first term is 1/5. So you come back here and ask yourself, well, how am I going to get positive 1/5? Well, the way that's going to I have to start at 1, because if I start at 0, my first term would be negative. Okay? So the radius of convergence is 5. Interval of convergence, again, we're back to, do we get to include the 0 or not? So now we're plugging it into the derivative function. Again, that's negative 1 to the n minus 1 and 5 to the n minus 1. This gives out negative 1 to the 2n, which is always even, which is positive. And then you're left with just this, and by the nth term test, that diverges, etc., etc. For part C, they want the second derivative. So here is our first derivative. So for our second derivative, this whole black thing here is just a constant. We're finding the derivative of x minus 5 to the n minus 1, which is n minus 1 times x minus 5 to the n minus 2. Term by term, the derivative of 1/5 is 0. The derivative of the next term is negative 1 over 25. So if you want to start with negative 1 over 25, in order for this to be 25, we would have to start at n equals 2. It kind of goes up 1 each time, but be careful of that. Okay, radius of convergence still 5. It's somewhere between 0 and 10, and again, you'd have to check at 0 and at 10 in the second derivative. Now, here's the original f of x again. This time we're going to integrate. So again, this whole thing has no x's in it, so that's just a constant. We're integrating x minus 5 to the n. We get x minus 5 to the n plus 1 over n plus 1. As far as integrating term by term, this would give us 1/5 x minus 5 squared over 2. The next one would give minus 1/50th x minus 5 cubed over 3. So again, if you kind of leave that blank, you realize that your first term should be x minus 5 squared over 10. So in order for that to happen, it has to be starting at 1. So you get it, your x minus 5 squared. You get 1 times 5 to the 1 times 1 plus 1, which is your famous 10. And of course, 1 plus 1 is 2, and there your first term will be positive. Again, same radius of convergence of 5. And again, you'd have to check at the endpoints, but it's going to be 0 to 10. Okay, the series represents a well-known function. Use a computer algebra system to graph the partial sum S10 and identify the function from the graph. Okay, so this actually is the sign of x, and what they want you to do is to just enter this and stop it at 9. Okay, and the reason it's 9, not 10, is because we're starting at 0. So 0 to 9 would be 10 terms. Okay, so what should happen is when you graph sine of x and when you graph this, they should overlap almost completely near 0, because this is a Taylor series at 0.